Okay, so let's start. Welcome to this course on deep learning. This is mainly EE6380, but also offered under AI 5100 and AI 2100, mainly for AI students. Um, so we'll start with some basic logistics of the course. So the prerequisites of this course are you should have a strong foundation in probability and linear algebra that is expected out of everybody. Also, either PRML or FOML is a strict prerequisite. Either one is okay. I think there were some issues for people trying to register with FOML, but hopefully that should have been resolved by now. If you haven't tried so already, you can try it later. Try to register for the course later. Also, you're expected to be fluent in some amount of Python. I don't expect you to know very advanced stuff, but at least basic NumPy, Matplotlib, to the level where you can implement, say, linear regression or a linear classifier from scratch, right? Um, it's also helpful if you've taken a course in some statistical learning theory or convex optimization. It's not a prerequisite, but you'll find some things easier if you've done one of these courses. I'll introduce whatever concepts are necessary for this course, but in the end, I will not have the time to cover all of the background required. So part of the intuition and some background will be available to you if you've taken these courses. All right. And logistics wise, there's a course page. This is you can get to the course page by going to my homepage, clicking on teaching and deep learning. So I'll be posting details about the course assessment and some reading material and so on in this particular page. So just watch out for some stuff here. So the assessment at this point is tentative. I'll refine this in maybe a class or two, depending on how many people register for the course. But you may expect maybe around 3 exams and some programming assignment. There may be a project, but I'll confirm that in maybe a class or two. There will be some surprise quizzes. I won't announce in advance when it's going to be held. It will be mostly a pen and paper based quiz. In case you're planning to audit the course, then you must turn in assignments or exams. You should secure whatever is required to get a pass grade. And of course, if you just want to sit through the course, you're more than welcome to do so. The slot is fixed. It will go on in slot S. There's no possibility of a change at this point. And this will be the class menu. Again, there are a bunch of references. I'll keep updating these as we go along. But I will not follow any one particular book. I'll pick topics from different sources, not even these books, maybe some papers and so on. At this point, deep learning, there is no one single reference for deep learning. The field itself is moving on pretty quickly, so there's no one good reference. But this particular book by Bishop is good at a high level because it presents some of the latest stuff in the field, but not in a lot of detail. The second reference is also pretty good, but it's a little old at this particular point, but it's good for the fundamentals. The third book is very up to date, and it tells you how to build all sorts of machine learning and deep models from scratch. It doesn't get into a lot of the theory, but it's an excellent reference. There's an online link. It's available not just as a PDF, but it's a whole website in itself, and it keeps getting updated. So it's an excellent reference. It's very nice if you want to get started. For the first part, mainly for the theory, I'll be following these two books, Understanding Machine Learning by Shai Shalev Schwartz and Shai Ben David. It's again a very good book to learn the basics of machine learning, and we will use some of those concepts in this course. I'll speak more about that in the next couple of lectures anyway. The second book is a little more advanced, but it's a very nice and thorough reference if you want to get into learning theory in particular. And if you want to recap your basics in probability and linear algebra, then here are a couple of references. There are also a few references if you want to read up on optimization beyond what we will cover in this particular course. There's a tentative list of topics that I'll go through. I'll also upload slides and class notes on Google Drive. Links are going to be available over here. Some of the lectures are going to be recorded, and whatever is recorded properly will be uploaded in some YouTube playlist. Again, links will be provided here. So please go through this particular course webpage, and if you have any questions, please let me know. We'll take academic honesty and plagiarism very seriously. You're not any sort of malpractice will not be tolerated, and any form of malpractice in exams will result in a fail grade. All right, and we'll also maintain timelines for homeworks very strictly. There won't be any extensions or deadlines provided. All right. Okay, let me get back to this. So while a lot of the references will be updated in that public page, we'll also use Moodle for off-class discussions, particularly for assignment submissions and announcements and so on. You can find the link to the Moodle page on this website itself. So there's a link provided. You can log in using your IIT Hyderabad email. This is accessible only within campus. If you want to access it outside campus, then you must use a VPN. Okay, so there's also an enrollment key which will be shared separately with people who registered. But let me also maybe just write down the enrollment key. So in case you've not registered for the course formally and just want to sit through it, you can just take this enrollment key and join the Moodle. All right. Okay. So this is a course on learning and artificial intelligence, and there is a tendency to use a lot of AI. When I say AI, I'm talking about LLMs in particular, like ChatGPT or Claude or whatever. And I thought that I need to say something on this. So remember that AI is a very useful tool, but what you should really focus on is on learning and not the end result. AI can help you produce the end result very quickly, and it may seem a lot easier to do a lot of things through AI rather than putting in the effort yourself. But it's not going to help you in any way. All right. So you should learn to use these AI tools like Claude or ChatGPT and learn to use them well for work. But when you want to learn, it's sometimes detrimental to your learning because it's easy to just ask a question and get the answer directly rather than think about the problem itself. For example, if I give you a homework assignment, the easiest way is you just ask the AI to solve it for you, right? So you get the solution quickly and easily, but then you don't learn anything. This is particularly for, say, programming assignments, right? So it's important for you to spend time to do things without AI. So whenever you are faced with some sort of a challenge, you don't understand something, try to look up the references. It's AI can be very useful. You can ask it specific questions that maybe you don't understand a particular concept properly. You want to clarify that. You're always welcome to talk to me, of course, but you can also use AI to answer some of those questions. But I would recommend you to not just ask it the final answer, but also go through whatever reference it may have used in order to produce that particular answer, because you get to know a lot more than just that end result. Right? And you're not permitted to use AI for homeworks unless I explicitly mention it. Right? And as I said, heavily using AI to do your classwork may bring you benefits in the short term in terms of a grade, but in the end, it's going to be detrimental to you. Right? You don't learn anything. And the most important thing is that at this stage, you need to develop your critical thinking skills, which don't really improve if you rely heavily on AI. It is that process of thinking about a particular problem deeply that lets you improve. Right? And try to focus on that rather than just getting the end result. Okay, so now before we proceed, any questions related to logistics? Questions? Okay, so in that case, we'll start with the material itself. So I'll give a very brief history of some salient uh, results which made deep learning so popular. Right? So deep learning itself has a very long history. In a sense, you can identify the origins of deep learning from the perceptron, which was proposed in 1958. And there was a not much happening until maybe 1986, when there were algorithms that came up that allowed you to train multi-layer neural networks efficiently. Beyond that, again, although all of these algorithms were present at the time, although some of the ideas were still there, it was not efficient, it was not practical to do many of these things. So it was only around the 1990s when, in some sense, deep neural networks got some sort of an impetus. And but really, the major breakthrough came in 2012, when it was found that, okay, so up to this particular point, the idea in deep learning was that you try to identify, you need a lot of domain knowledge, you use that domain knowledge to identify features, and then use those features in order to learn what you want. You want to develop, say, a classifier or a regression algorithm. You try to identify or extract features that are going to be specific to the problem that you want to solve, and then try to design a learning algorithm that operates on those features. So that was the state of the art, and those were the ideas that prevailed until maybe around the 2010s. But beyond this point, there was a paradigm shift. Instead of manually identifying features, which required a lot of domain knowledge, people said, okay, let's not worry about the domain knowledge at all. Let's say that I just take a lot of data. Right? I collect a lot of data and I design an algorithm, a fairly generic algorithm, and then see how it works. And surprisingly, it worked very well. Right? And that was the point where deep learning took off. The ideas were still there, but it was not very efficient to do so until this particular point. So there were some algorithmic ideas that came up around this particular time, which enabled deep learning to take off. And then there were a bunch of other interesting results that happened and so on. And it was only about 2015, 2016 that the applications of deep learning really took off in a major scale. And in 2017, there came a new architecture called the transformer, which allowed us to have these large language models and many of the other AI tools that we see today. So in 1958, Rosenblatt proposed this perceptron, which was this huge machine, which was essentially just a linear classifier. Right? Again, remember, this is way back in 1958, where there's not a lot of compute available. For right now, this may seem like a very trivial thing to do, linear classification. But at that particular point, it was a major breakthrough. And this was essentially designed to do supervised image classification. So the kind of experiments that he ran, where he took a piece of paper and then you draw very simple shapes, it essentially was a binary classifier, and it could distinguish between shapes, different types of shapes that were drawn. But as we know, linear classifiers essentially work well only if the data itself is linearly separable. And that's where the perceptron failed. So even a single layer perceptron can't learn even a simple function such as the XOR. Right? So at this point, there were a few developments, and it was later shown that multi-layer perceptrons are good and they can learn a lot of functions well. But then there was no efficient way to train a multi-layer perceptron. The advantage of this simple perceptron, simple linear classifier, was that there was a very efficient gradient descent type of algorithm that allowed you to train the perceptron. A multi-layer perceptron, on the other hand, is nice. You can implement it, but at that particular point, there was no way of efficiently training this. So it was in 1986 that Rumelhart, Hinton, and Williams came up with this backpropagation algorithm, which was the major shift and essentially brought about deep learning. So you have multi-layer perceptrons, which are good and can learn a lot of functions. But then how do you train them efficiently? And the backpropagation algorithm, again, we'll go through all of these in a lot of detail. But at a very high level, what backpropagation does is it's just a clever use of the chain rule. It uses the chain rule that allows you to compute gradients for multi-layer perceptrons efficiently. And again, as we'll see in this particular course, gradient descent on such multi-layer perceptrons is not a very easy task, because it turns out that the function that you want to minimize turns out to be highly non-convex. And that is one of the main challenges that arise in deep learning. So there are a lot of other developments that took off in parallel, but different architectures were proposed going beyond the perceptron. And in around 1997, the long short-term memory, or LSTM networks, were proposed in order to solve some particular problem. And they were extensively used, a very popular technique used in speech and audio signal processing. So they sort of dominated the field for a while. And in 1998, another architecture called the convolutional neural network was proposed. And again, we'll go through this in detail. But what you should keep in mind is the size of the neural networks that were trained at this particular point, right? So the kind of neural networks that were proposed in 1998 were neural networks with around 60,000 parameters. That was the state of the art at that particular point. And these were the size of the neural networks that could be trained on, say, consumer level hardware. Well, not maybe consumer level, but let's say research level hardware. And again, until this particular point, and even beyond this, the idea was that you have an image, you try to extract certain features. This could be some kind of a DCT or a wavelet transform, and extract certain coefficients of the wavelet transform, and then feed that into the neural network and train the neural network in order to learn a classifier. So that was the general approach that was used up to this particular point. But around the 2010s, people wanted to go outside this, because it's very difficult, right? For one particular problem or one particular data set, you know what kind of features you want to extract. But let's say I give you a different data set. So instead of images which have cats or dogs, I give you an image which has maybe different types of clothes, and you want to distinguish between them. Do you have to learn a completely different set of features for this? Do you have to extract a different set of features for this? That's not very efficient, right? So around the 2010s, people said, okay, let's forget about this feature extraction approach. We just feed the image directly to the neural network and then have it learn whatever features it needs to learn. Again, this was not an idea that came about. This was an idea that did prevail even before that, but it didn't work very well. But around 2010, particularly this particular work by work called AlexNet, this designed a huge neural network. Remember that in 1998, the number of parameters used in the neural network was around 60,000. This was a huge jump to around 60 million parameters. And at that point, there was no efficient way of training a neural network. And if you go back to around 2012, the number of parameters was so large that you could not even fit the entire model on a single GPU. So this required a lot of algorithmic ideas, which allowed you to split and train the neural network using multiple GPUs. So there are a bunch of different engineering techniques that came about in the 2010s that made deep learning possible. All right. And for many of these innovations, all of these came about because there was sort of a competitive environment. So around the time, there were these competitions held in conferences like CVPR and so on, which asked people to design the best neural network for a particular data set. And one very popular data set was the ImageNet data set, which is a bunch of images with I think around 100 classes or so. And progressively, there were different subsets of these data sets which were used. And at that point in 2012, this AlexNet beat the second best performing neural network by a huge margin. So in some sense, this was a threshold that no one was able to pass, and AlexNet beat that. So all of that was essentially supervised learning. But then deep neural networks were also found to be excellent for generating new images. So let's say I want to generate a new image of a person, right? A person who doesn't exist, but it should look like a real person. Right? So that's the goal behind generative modeling. And the nice idea that came about in 2014 was the following. Well, let me train two different neural networks, one that generates images and one that distinguishes between whether this image is a real image or a fake image, right? So I have a neural network that takes pure noise as input and outputs a fake image. And then I have a data set of real images. Maybe these are images of actually real people. And the goal is to design this generator which takes pure noise as input and outputs an image which is fake, but it looks very realistic. And so how do you design this generator? Instead of designing it independently, you also design a discriminator, another neural network which is trained to distinguish between fake and real images, right? And then you train these simultaneously. So now there's a game or a competition between the discriminator and the generator. So the discriminator wants to, so the discriminator is not told which of these two is real or fake, and it has to learn it separately. And the generator just has to generate the fake image. So there is this particular loss function which became famous at that particular point. But the goal is to design the best discriminator and the best generator. And this becomes a minimax game. And at the end of training this generator and discriminator together, it turns out that the generator can actually produce something that looks very realistic. And there were other architectural improvements, particularly with this idea of introducing skip connections. We'll see that in a little bit. And again, what I want to maybe highlight is this large-scale visual recognition challenge, which was one of the major competitions which which brought about a lot of innovations in computer vision. So at this particular point, a lot of the applications and the effects of deep learning were mainly seen in the research community and to some extent in the industry. But I guess deep learning became very popular for the general public because of AlphaGo. So around 2016. So up to 2016, chess was a game that for which you had very good algorithms, which could very easily beat the best human chess player, right? Because the difference between chess and maybe some of the other board games is that the number of possible moves that you can make in chess is fairly limited, not too large. It's large, but for a computer, it's not too large. So a chess engine can essentially try to look at all possible moves it can play for the next, let's say, 10 steps or 20 steps, which will become like a huge tree, and it can try to search for the best possible move it has to play for the next round. So that was the main idea behind chess. And even at this particular point, chess engines that can run on your phone can essentially beat the best human player, right? So that was solved. Many other board games were solved, but one major board game, which was very difficult for similar engines to beat, was Go. And the problem with Go is that there are a huge number of states. There are like 10 to the 170 states, and it's impossible for an algorithm to search for the best possible move. So it turns out that you can design a good algorithm for Go by training a neural network to play on its own. So you instantiate two different versions of the neural network. It plays against itself, and then you keep doing this. So you initially start with human games. You make it play with human. You make it play against a human, and it tries to do some form of reinforcement learning to learn what is the best strategy. But beyond a certain point, it just plays with itself, and it keeps improving. And it turns out that it improved to such an extent that it could beat the best player in Go at that particular point. All right. There was, I guess this was, I don't know, AlphaGo 1 or whatever they called it, but there was also another version where it purely learned to play on its own. There were similar other variants that were introduced for other games. I don't know if you were too young at that particular point, but there was a game called Dota, and there was the same company that designed AlphaGo, DeepMind, also designed an algorithm to play these online multiplayer games. And again, all of these were trained in the same approach. Essentially, the learning algorithm plays against itself. Initially, it does very dumb things. It tries to figure out what it has to do at the next step. It doesn't even know the rules. All right, it's allowed to purely explore whatever it can. So initially, it's extremely bad, but then it's a machine, so it can learn much faster than a human, and it can essentially go on 24 hours a day, right? And it turns out that if you train it well enough and you put enough compute into it, it can beat the best human players. So all of these were sort of popular techniques that were used, but around 2017, there was a shift in architecture. So up to around 2015-16, different kinds of problems require different architectures, right? So if you have a vision problem, you use a convolutional neural network. If you have some sort of sequence learning problem, you use a recurrent neural network or something else. So each person wanted to introduce a different architecture for a different problem. And I guess in 2017, that was kind of unified by this architecture called the transformer, which eventually turned out to dominate all areas of deep learning, ranging from vision to language models and others. All right. And the transformer, in its original avatar, it was designed to do next word prediction. You're given a sequence of text, and you want to predict what is the most likely next word in that particular text. So it sounds like a simple problem, but it's extremely challenging. And this particular architecture beat everything else before that. And this particular architecture is the basis of all of the large language models that we see today. So another major breakthrough, again in terms of applications, came into 2020, 2021, again for different challenging problems. In biology, there is this problem called protein folding, where you want to predict a protein's 3D structure from its amino acid sequence. This was known to be a very challenging problem, and there was no algorithm that did well up to that particular point. So you can verify what is the correct structure by experiments using some form of like crystallography techniques. But there was no algorithm that directly took the amino acid sequence and predicted this 3D structure of the protein. And again, it came from the same group, DeepMind. They designed an algorithm called AlphaFold. There was AlphaFold 1, I think, in 2020, and AlphaFold 2 in 2021, which completely beat the state of the art by a large margin. And in fact, for this AlphaFold 2, the main leads, Demis Hassabis and John Jumper, they received the Nobel Prize in Chemistry in 2024. And as we know, from 2020 onwards, we've seen large language models, which are essentially a variant of the transformers, which are essentially trained to just predict the next token. You start with a basic algorithm which all it does is just try to predict the next word in the sequence or the next token in the sequence. And building on top of that, you have ChatGPT and Claude and all of these other variants. All right. Okay, so this was a very high level overview of deep learning or motivations to study deep learning. But again, it depends on how, since this is a semester long course, we can't cover everything that there is to learn in deep learning. And the goal of this particular course is to provide the fundamental ideas behind deep learning. You won't be able to design a state-of-the-art deep learning model. It's too much for us to do in a particular course, and we don't even have the resources. If you want to do cutting-edge LLM work, you should be really working in no one aside from a frontier lab can afford to work on these large models. But nevertheless, no matter what they work on, the fundamentals are still the same, whether you're training small-scale deep neural networks or large language will be at least for parts will be a little bit different from other courses on deep learning because we want to focus on the foundations. All right. So generally, deep learning is taught as a series of different architectures that you have to learn. But we'll start with the foundations of statistical learning because there are a lot of ideas that are used in deep learning. The common complaint is that deep learning doesn't have any theory. It's all just trial and error, right? Which is not really the case. There are a lot of unintuitive things or counterintuitive things that happen in deep learning, and deep learning practice is very different, is in fact quite different from the theory that has been developed on machine learning. But many of the practical considerations and many of the ideas, the heuristics that are used in deep learning come from strong foundations, from ideas that actually arise in machine learning theory, but then maybe tweaked a little bit. Or there are some sort of counterintuitive phenomena that happen in deep learning, which you would not expect to happen based on predictions from machine learning theory. So in this course, we'll try to clearly distinguish between the two. What is rigorously well established and high-level heuristic ideas that seem to work, but nobody knows why it works, right? So it's also important to know why something works when you can explain it, but also identify what kind of engineering optimizations one had to do, and things seem to work anyway. Right. So we'll start the course with these learning theory roots, We'll try to identify what part of these ideas are rigorous and what parts are purely heuristic in nature. So there will be a fair amount of math in this course, but we'll also try to understand how to build things from scratch, right? Um, because we want to cover a fair amount, the course will be quite fast-paced, but you should always stop and ask questions at any point in the course, right? Here are some tentative contents for this particular course, and we'll see how much we can cover in the course. So again, deep learning is used for a large number of problems in many applications, and it's not possible to go over everything. So we'll focus on 3 classes of problems in this particular course and not touch anything else. So the first will be very simple supervised learning, and we'll spend a bulk of the time on supervised learning, which majorly will be classification. And using these ideas, we'll also talk about 2 other problems. One is generative modeling, which is similar to the GANs that I talked about earlier, and sequence modeling, which is the basis of large language models. And we'll try to spend a little bit more time on this sequence modeling. Here are some tentative contents. I'll start with some basics of learning theory. If you've already taken a course on statistical learning theory, this will essentially just be a recap or a very quick overview of the course. And we'll do a little bit of optimization before we get into deep learning. In particular, I'll talk about the main challenges in optimizing deep neural networks and a very basic stochastic gradient descent algorithm and its analysis, and also about backpropagation and automatic differentiation, which is a more generalized version of the backpropagation algorithm. And then we'll focus on classification. Specifically, we'll try to build a classifier and see the ideas behind building a classifier. And hopefully at this particular point, we should cover this at least close to the state of the art in 2012, right? The AlexNet that I mentioned. We'll mostly follow, we will use the PyTorch framework for all our programming. And we'll see how to build these basic classifiers, both using logistic regression and some basic neural networks from scratch. And then we'll talk about, we'll do a slightly more deeper dive into the state-of-the-art optimization algorithms for deep learning, specifically variants of stochastic gradient descent. Vanilla stochastic gradient descent doesn't do very well, and there are other ideas, other algorithms like Adam, which is a very popular algorithm. So we'll get into the details of Adam and variants of these algorithms. And then we'll talk about specific architectures, feed-forward and convolutional neural networks, and how you can improve these to get something like AlexNet. After that point, we'll talk about sequence modeling in some detail and some of the ideas there. And then we'll spend a fair amount of time with the transformer architecture and state space model. So deep learning borrows a lot of ideas from traditional signal processing, because even the convolutional neural networks were heavily signal processing inspired. In fact, convolutional essentially comes from the convolution filter, and many of the basic blocks that arise in a convolutional neural network can be thought of as filters that are used in electrical engineering. And again, there has been another resurgence in these language models called state space models, where control theoretic ideas are trying to be used in order to design these LLMs. And we'll spend a little bit of time on language models, some of the challenges that are there. What exactly is the language modeling problem or the next word prediction problem, and some of the ideas that are used in order to train a large language model. Again, all of these last topics depends on how much time we have at the end of the course, but I'll still try to cover it in some amount of detail. And we'll also do a little bit of generative modeling. maybe spend a little bit of time on generative adversarial networks and diffusion models, which use a completely different principle than anything else that we see in the course. So this is a very high level overview of the course. Any questions up to this point? Okay. So, I mean, just to get a sense of the background of everybody in the course, I guess everybody has done either PRML or FOML. Have you trained a neural network before? If you have, just raise your hand if you've trained a neural network at some point. Right? And what did you use to train a neural network? Was it something like, did you use a framework like PyTorch to train the neural network, or was it done from scratch? Okay, so everybody who did it from scratch. And what kind of neural networks did you train? Was it just a feed-forward neural network? Okay. How many of you have not heard of feed-forward or convolutional neural network before? Okay, that's good. How many of you have seen the stochastic gradient descent algorithm? Okay, good fraction, but not everybody in the course. That's fine. Okay, and did you see an analysis of the SGD algorithm or convergence of SGD or results on convergence of SGD? Okay, fine. And did you learn about empirical risk minimization in the course? How many of you have heard of the term empirical risk minimization? A smaller number this time. Okay, that's good. Never mind. Okay, so let's. Okay, so in the next couple of lectures, I'll focus on supervised learning. All right, and mainly from a very high level theoretical perspective. So we'll mathematically rigorously define the supervised learning problem, see what can be done and what cannot be done in supervised learning, and some of the learning theoretic ideas from statistical learning theory that have been developed for the problem of supervised learning. And in this particular discussion, we'll not focus on how do you actually design an efficient supervised learner. We will not worry about that at this particular point, not yet. All right. But try to see if we didn't have any constraints on computation whatsoever, and our only limitation is perhaps in the amount of data that is available, then what is the best possible that we can do? Right? That's what learning theory tries to address. Right? Forget about computational constraints. You're allowed to design any algorithm that can run for however long you want, but all you are provided is data that is kind of well behaved and models the problem at hand. Given these restrictions, how well can you learn something, right? So prototypical examples of supervised learning are classification and regression. So you're given an image of a handwritten digit. That's a classical problem. And the goal is to design an algorithm which takes the image as input and outputs which digit was present in the image. A regression problem is basically one. For example, you're given some data, some demographics and maybe air quality data, and you want to predict the price of a house in that particular neighborhood, right? So here in classification, you have the number of possible outputs is finite. In this case, digits can vary from 0 to 9. So there are 9 possible outputs that your algorithm can give. and the goal is to give the output exactly every time. And in regression, the house price can be any number between, say, within a certain range, and you can't get it exactly, and the goal is to just get it approximately close to the actual value. Again, I'll make this formal as we go along. So in all of these problems, all you have about the problem itself is some sample data. For example, in classification, you're given a bunch of images that are labeled. So there are images, for example, what you have on the right is a bunch of images of digits from 0 up to 9. So you're given this bunch of images, and the goal is to design an algorithm which learns the relationship between the pixel values in the image and the actual number that is present in that particular image, right? And such that if you're produced a new image not from this particular set, then it can identify the correct number correctly, right? So given sample data, we want to learn the relationship between the input and the label or the output. So let's now get into the technical details. So what we have essentially is there is some ground truth which tells you what is the relationship between, say, the image and the label. When I say label, it's so in the context of in the context of this particular problem, the label is the number that each image corresponds to. So there's some relationship between x and y. We'll refer to x as the feature and y as the label. It's common terminology that we'll use throughout whenever we talk about supervised learning. And we use the same terms irrespective of whether we're talking about classification or regression problems. So there is some underlying relationship between x and y, and we make an assumption that this input-output relationship is specified by some joint distribution between x and y. Okay, if the x and y are continuous variables, then this could be described by a probability density function. If the values that x and y can take are discrete, then it's specified by some joint probability mass function. Okay, the crucial point is that this joint distribution is not given to us. We don't know what the joint distribution is. But so a special case of such a joint distribution or a relationship is what I call the realizable setting, or a concept class, where x is random. It's drawn according to some distribution, and the relationship, or how you get the label from x, is through some unknown function. So for example, if I go back to this problem of classifying images, right? I'm given a handwritten image of some digit, and my goal is to output what digit is present in this particular image. Right? So in this case, there's a clear, well-defined relationship between the input and the output. If it's a 0, then the output is definitely going to be, if it's drawn as a 0, then it has to be, these pixels correspond to the number 0 every time it is fed. Right? But on the other hand, there can be problems where you don't know there is some maybe hidden variable which is not present, which is not available to you, and x is not sufficient to completely determine y. In which case, there's no function which tells you what y is given x. So the relationship between x and y need not be deterministic. That's all that I'm saying, because of some other underlying hidden variable which you may not have access to. And that is why we look at a joint distribution instead of specifying the relationship between x and y through some function. But in either case, whether it's the realizable setting or this more general setting, x is random, and either the joint distribution or this function is completely unknown. You don't know anything about these. So what are we given? What do we know about the problem? All information that we are given is a labeled data set. So you are given a bunch of n points, which are samples or features, along with the correct labels. Right? So how do you get this particular labeled data set? In the example of, say, the handwritten digits case, maybe somebody has painstakingly drawn these things. You take a piece of paper, you get a bunch of people to write 0 up to 9, and then collect all of these to form a data set. That's typically how it's done in many problems. So you collect a lot of data and you have somebody manually identify what the correct label is. And the other assumption that is made in learning theory is that in this labeled data set, these endpoints are all independent and identically distributed. That's a crucial assumption that you always have to keep in mind whenever you're designing a supervised learning algorithm. It's not always true in practice, mind you. There are many cases where this data set is not IID. There could be some kind of dependence because maybe of the way you have collected this particular data. All right. So this is what is given to you. You are given a labeled data set, and your goal is to design a function that predicts the value of y given x. Right. So the goal is design some function h from the feature space to the label space, which predicts such that h of x is your prediction, and you want this prediction to be as close to the ground truth as possible. That's the goal, right? We'll impose another restriction. We could always say that h can be any function you choose, right? But then we'd also define this other notion called the hypothesis class, which is the class of functions that your learning algorithm can actually output. Right? Instead of saying that h can be any arbitrary function, we'll say that h is some restriction. You impose some restrictions on h. For example, this hypothesis class could correspond to all possible linear functions, or h could be the class of all polynomial functions of maybe a certain degree or any degree you want. Or h could be the class of all two-layer neural networks with a certain number of neurons. Yeah.
In there, we assume the IIT.
Yes.
So are we assuming all the digits in the case of digit classification? Are we assuming all the digits will come from the same distribution?
We are saying that all of it comes from this. There's some underlying distribution which generates the images and the classes corresponding to it. So in the context of, let's take the digit classification problem, let's assume that there is a well-specified function which is unknown to you, but given an image, it tells you that function outputs which digit it should be. Now, in this case, we assume that the image is drawn from some distribution, and that distribution is fixed throughout our throughout the formulation of the learning problem, and all of these samples are drawn according to that particular distribution only. It's not that some samples are drawn according to one distribution and some samples are drawn according to a different distribution.
That distribution will be able to generate all the 10 digits.
Correct. So there's some distribution which can potentially generate all 10 digits. No. So everything is coming from one distribution. But one thing you have to keep in mind is that maybe the distribution is such that not all of the digits are equally likely to occur. Maybe because of your data generating distribution, 0 is more likely to occur than 3. That can happen, which is fine, right? But the only requirement that we'll have is that all of these are IID. Again, keep in mind that this is a mathematical formulation. In reality, in practice, there are a lot of deviations that are observed, but we can only derive a theory by making some assumptions. And these are the assumptions that we will work with. There are a lot of theoretical results which analyze what happens when these assumptions deviate. What happens when this is not when these are not independent. or when they're not identically distributed. There is a theory behind all of that, but again, for the purpose of this course, we'll assume that it's this simple setting. And this itself will bring about many of the basic concepts that we require to go through the rest of the course. Right? Yes.
Can it also happen that this data set we have doesn't belong to any system? Doesn't belong to any system.
So that's the Bayesian versus frequentist interpretation. All right. So given a data set, in practice, what do you have? You have some data set, right? So how do you model this particular problem? One way of modeling this problem is that, okay, these are some arbitrary set of images, and your goal is to understand or learn the functional relationship between these. This is usually the frequentist approach to statistics in general. This is the Bayesian approach, where you assume that there is an underlying distribution, and what you observe is part of that particular distribution. As I said, this is a mathematical formulation, and depending on which mathematical formulation you use, you get a different set of results. Okay, so this is an assumption. It is a strong assumption, and you derive some results based on these assumptions. Assuming that all of these hold, what can we do? You develop this theory and then apply it to practice and see how well it performs. So in the end, the validation has to be on your real world problem. But to develop the theory, we'll make use of these particular assumptions. Okay, that's why we make these general assumptions that there is some joint distribution, but we don't know what the joint distribution is. Because if we assumed what the joint distribution was, then you're actually putting in a lot of bias. Because in practice, what you see, observe, maybe you develop a theory where X is assumed to be Gaussian. But in real world, maybe it's not, it doesn't behave like a Gaussian distribution at all. Good. Any other questions? Okay. So you're given this labeled data set, and the goal is to design a classifier or a regressor or some supervised, or more generally, we'll call H a predictor. And instead of taking arbitrary H, we'll impose some restrictions on the kind of H that we can choose. We'll also see why we have to impose a restriction in a little bit, but we'll say that H can only come from this hypothesis class script H. Okay, so this is part of the problem definition itself. You have some. We'll see that we have some room in choosing this particular hypothesis class. In practice, the problem is completely defined by this joint distribution and the data set that you're providing. Okay, and your goal is to choose an appropriate hypothesis class and choose a H from this hypothesis class that does well, that tries to learn the relationship between X and Y. Okay, that's the high level problem. Any questions? Okay, so now let's formally define this. So as I said, a learning algorithm is any algorithm that takes this data set and the hypothesis class as input and outputs a predictor from this hypothesis class. So any algorithm that does this will be a learning algorithm. It may be a good learning algorithm or a bad learning algorithm, doesn't matter. For example, a trivial learning algorithm is something that outputs the same H irrespective of what the data set is. It's a dumb learning algorithm, but it is a learning algorithm nevertheless. But in the end, what we want is a good learner, right? So how do we measure the performance of a learning algorithm? And typically to do this, we have to define some measure of performance, and such a measure will be called a loss function, right? The loss function is some function which takes two different labels and outputs a real number, typically a non-negative real number. And the loss function is such that if the two labels are the same or if they're close, then it has to be small. If they're very different, then it has to be large. Those are the only restrictions that we'll impose on a loss function for the general setting of the problem. Okay, so one example of a loss function is the 0, 1 loss, which is what defines the classification problem. So in this case, L of say y prime, this is equal to 0 if y is equal to y prime and it's equal to 1 otherwise. So basically, if let's take the problem of identifying the digit in the image. If the true digit is y and what the digit that you have predicted is y prime, if you predict the correct digit, then you incur a loss of 0. If you predict it wrongly, doesn't matter which other digit you predicted, then you incur a loss of 1. All right, that's the 0, 1 loss. Another could be, say, the typically the L1 loss or the absolute error loss, which is L of y prime, assuming that y and y prime are real numbers. This is equal to mod of y minus y prime. All right. So again, if you had to use this for the digit classification problem, then you could say that if the digit is close to the digit you predicted was far away from the digit that you had from the actual digit, then you incur a higher loss. So typically in classification, you never use anything else apart from the 0, 1 loss. And whenever I say classification, I will implicitly assume that I'm only talking about the 0, 1 loss. So in a classification problem, we want to get the correct label exactly, not just approximately. And similarly, there's the squared error loss or the L2 loss, which is L of y comma y prime is just y minus y prime the whole square. So there's a whole bunch of different loss functions that you can consider, and we'll see many of them later on. But these are some simple examples of loss functions that we look at. So we want to design a learning algorithm that outputs a predictor which incurs a small loss. Right? But what does it mean to incur a small loss? We want this to incur a small loss on another sample that is outside the set of samples that we have seen. Right? Going back to the definition of the problem, we have this labeled data set, which we'll sometimes call the training data set. So if we get samples outside the training data set, then we want to incur a small loss. We want to, because there's no point in just doing well within the data set. You want to do it on a completely different problem, right? So, and how do you measure the performance? The performance is measured through the expected loss, where this expectation is taken over this joint distribution Pxy. All right, where this x comma y is independent of the training data set, but it has the same distribution as the training data set. So this is where the distribution plays a role. If let's say you have a training data set that's drawn from one particular distribution, but in practice, when you're actually testing it out, if the data that you have in practice is coming from a different distribution, then no guarantees, right? We assume that both the distributions are exactly the same, and that's crucially important. So this performance on a completely random input in expectation is called the population risk or the generalization error. All right? And this is a term that will keep occurring throughout this course. The goal is to design a learning algorithm which minimizes the population risk or minimizes the generalization error. Okay. In practice, I mean, the generalization error is defined in terms of this distribution Pxy, which is not given to you. So how do you evaluate the generalization error? In practice, what you do is you have a separate test set, which is drawn according to the same distribution. And then you take just the empirical average of the loss in over that particular test set, and this will approximate this generalization error. Okay, so that's what you do in practice. But in order to develop a theory, our goal will be to design a learning algorithm that achieves as small a generalization error as possible.
How do we make sure the testing data that we are testing
Yes.
follow the same distribution it has been taken practice?
Okay, in practice. So one thing that you have to do is when you collect your training data, you have to make sure that it's taken under the same conditions as how it will be evaluated. Right? Let's say, for example, if you take the example of, say, designing an autonomous driving car. Okay, it means that if you want to ensure that it follows the same distribution, it has to be all of the data that you collect should be under the same conditions as the real world. It's not that you take data in a on a completely empty road in an idealized environment and then employ that in a, say, in the national highway, right? So that's what it means, practically speaking, conditions. But then when you do experiments, what do? What you typically do is you have a bunch of images, right? You randomly take a portion of it as the training data and another portion and the remaining as test data. If you're sampling them randomly, then they will follow the same distribution. That's how you do it in experiments. But in the real world, when you're designing a learning algorithm that you want to deploy in practice, you have to make sure that the training data that you get is drawn in the same conditions as how the final algorithm is going to be used. All right. And that's also something to be kept in mind, right? Because there are a lot of scenarios where you can't get data from with the exact same conditions as how it will be used in practice. So then you have to think about ideas as to how do you adapt things. You draw it from a slightly different environment. You have a lot of data from a different environment, but in practice you see that there are other non-idealities that are present. So then you have to account for those non-idealities when you design your learning algorithm. And again, there has been a lot of work to address all of these issues. But again, it's not within the scope of this particular course. But that's a valid point, and that has to be kept in mind when you want to deploy these models in practice. Any other questions? Great. So some special cases of supervised learning algorithms, binary classification. Again, when I say binary classification, it's under the 0-1 loss. This is where the label set has exactly two different values. It's either 0 or 1 or cat or dog or whatever. Multi-class classification, where y is discrete, it's a discrete set, again under the 0-1 loss. Or the problem of identifying handwritten digits is a multi-class classification problem because there are multiple classes. And when I say regression, it's typically that y is continuous, usually taken to be some subset of R or Euclidean space, R to the D. Right? And in this case, you can have a general loss function. It could be, say, the squared error loss or the absolute error loss or something totally different. Okay, so let's try to think of specific examples of the entire problem itself. So let's take one simple example is the linear classifier. So just to make sure that we've formally understood the problem, if you want to define the entire problem, then you have to specify what the feature space is, what is X, what the label space is, what is Y, and what is the hypothesis class, and what is the loss function. So these 4 parameters completely define the problem. Okay, so you have to specify X, you have to specify Y, you have to specify the hypothesis class and the loss function. Okay, so let's take linear classifier for, say, binary classification. In this case, what is X typically? Yeah, it is, but what kind of a mathematical object? What set is it typically? Some Euclidean space. Usually, it can be generalized, of course, but generally, when you're talking about linear classifiers, it's some R to the d-dimensional Euclidean space. Y is R. When it's not R, we're talking about classification. So if I say binary classification, it's either 0 or 1. If it's if it has more than 2 classes, then it could be whatever the set of classes are. What is the hypothesis class? Okay, linear functions. A little more. Can you be a little more precise? What do you mean by degree D? Set of all straight lines. Okay. Can you give a mathematical function that y is equal to? Again, I want a mathematical equation that tells me what a classifier is. So h of x, let's assume that x is a d-dimensional real vector. It's some d-dimensional vector. So can you specify this in the form of an equation? So how would you mathematically describe this set of all? Okay, what does W transpose X plus B give you? What does what is the value of W transpose? What values can W transpose X plus B give you? It's a real number, right? But what do I want? I want either 0 or 1.
You can take, like, if it is positive, it can be, like, say,
So,
last one.
so to be completely precise, it's some indicator function of W transpose X maybe greater than or equal to B, or W transpose X minus B greater than or equal to 0, where W can be any real number or any d-dimensional vector and B in R. All right. Is this the set of all linear classifiers? Great. Okay. So where, I mean, hopefully if you're not comfortable with this or you've not seen this notation before, it's basically indicator of y greater than or equal to 0 is basically it's equal to 0 if y is less than 0 and 1 if y is greater than or equal to 0. In general, whenever I say one subscript some particular condition, it means that it's equal to 1 if this condition is satisfied and it's equal to 0 if that condition is not satisfied. I'll use that liberally throughout this course. Okay. And the loss function, it's the 0, 1 loss. So it's again in short form, it's indicator y equal to
One.
equal to not equal to.
Okay, yeah, sorry.
Right? So, so therefore, when I say linear classifier for binary classification, when I say linear classifier, it's typically it is binary classification. It's this is what the problem. This is what I'm talking about. It means that x is RD, y is 0, comma 1. The hypothesis class is this set of specific set of functions, and the loss function is exactly this. Okay. In this case, what does the generalization error correspond to? In fact, not just for linear classifiers, but for binary classification. So let me. So as I said, when I'm talking about binary classification, the loss is the 0, 1 loss. So the generalization error or the population risk, I'll use the notation R of some predictor. So H is your predictor. H takes an X as input and outputs a label Y. And R is a function of H because it evaluates the performance of that particular H. But this R also depends on the joint distribution Pxy, which is implicitly specified. So this R of H is the expectation of L of Y comma Y hat. Where this expectation is taken with respect to the joint distribution Pxy. I'm going to use Pxy irrespective of whether it's continuous or discrete. All right, it should be understood. So what is this equal to? Correct. So this is basically just the probability that y is not equal to y hat. So if you have indicator of some particular event or some particular condition, then the expectation of the indicator random variable is equal to the probability of that event occurring. That's a very nice property of indicator functions that are used like multiple times or in many ways in computer science and statistics and many other problems. Right? So basically, when I say I want to design a good binary classifier, it means that I want to design a predictor that minimizes the probability of error. Right? That's the specific reason why we choose the 0, 1 loss and not something else. Because we want to minimize the probability of misclassification. Okay, so that's one class of one hypothesis class. Let's see a couple of other examples. Say polynomial classifiers. In this case, I'll assume that the feature space is say R, and the label space is, say I want to just do binary classification. The loss is again just the 0, 1 loss. Can you tell me what the hypothesis class should be? Yeah. What is W and what is X? Okay, I mean, fine. You could restrict yourself to some degree K. Maybe let's call this H sub K, which is the class of all D at most K degree polynomial classifiers. It could be general, it could just be any polynomial. So how would you specify this?
Same
I understand what you're saying, but I want you to put it out more formally and precisely.
like using the linear function
Okay.
instead of that indicator with AKX power 3.
Okay. So one simple way is to say um, summation I equal to say 0 up to k, maybe alpha k x to the power k is greater than or equal to 0. That's one way of putting it. Alpha 0 up to alpha k are in R. Or I think a more compact representation, which I guess what you are trying to refer to, is you can say that this is equal to alpha transpose x is greater than or equal to 0, where your alpha is a k plus 1 dimensional vector, and your vector x is basically the vector x power k, x power k minus 1 up to x power 0. Right? Yes, transpose. The third and final example that we'll see is let's maybe take regression. Feed-forward neural networks or regression. Again, it's a fairly general definition. So in this case, let's assume that the input space is R to the D and the output space is R. Or the feature space is R to the D and the label space is R. What loss do you want to pick? Yep, squared error. Okay. What does the hypothesis class look like? Let's say this is the set of all two-layer neural networks. Basically, one hidden layer. What does it look like? How would you mathematically specify um, this particular hypothesis class? So what does a two-layer neural network look like? What do you have? You basically have a bunch of input neurons You have a bunch of hidden neurons and maybe a final output neuron. And all of these are, I'm talking about, when I say feed forward neural network, it's a fully connected neural network. So all of the neurons from one layer are connected to all of the neurons in the next layer. Right? And all of these connections, or the weights corresponding to each of those connections, can be chosen independently of each other. So how do you specify this mathematically? Is the question clear? So how do you get the values of the hidden neuron? Oh, composition of what functions? Okay. But how do you get it? Like, how do you specify it mathematically? Okay, fine. Let's say that the first layer is specified by some matrix W1. Okay, W1x, is it just W1x, or you apply some non-linearity? Let's call that, say, G1. Okay, so then it's some W2 followed by some non-linearity G2, right? So basically my h of x is the set of all functions that can be represented as G2 of W2. In this case, W2 is just a 1 by something matrix of G2 of G1 of W1x. Right. Let's assume that the number of neurons in this hidden layer is D1. So in this case, it's a set of all functions. So when I say a neural network with one hidden layer, it means that it's the set of all possible functions that can be represented as G2 of W2 of G1 of W1 times X. Right? Where W2 can be any matrix which is 1 cross D1. W1 is any matrix which is D1 cross D. And usually these nonlinear functions are component-wise nonlinearities. So G1 is a function from R to R, which is applied on every component. And G2 is a function from R to R, again applied on every component. Right? And this G1 and G2 are fixed and described by the hypothesis class. There's usually no flexibility in choosing G1 or G2. The only free parameters in this hypothesis class are choosing W2 and W1. All right. So if you go back to this definition of the hypothesis class, this one and the previous one and the one before, you see that the one before, you see that the hypothesis class can be described in many ways. It's a collection of functions which can be described using either geometrically or using some form. But this particular mathematical form explicitly brings out what parameters you can choose in order to pick one function from this hypothesis class. In this case, you pick a particular function, you describe one function by picking a value of W and B. If you fix W and B, then the function is fixed. right? But you're free to choose any W and any B. So these are all the free parameters that you have in order to choose one predictor. Similarly, for the polynomial classifier, you can choose alpha as you want, and these are all the free parameters. So this has k plus 1 free parameters. This has d plus 1 free parameters. And in this case, there are, how many free parameters do we have? It is d1 plus d times d1. Right? That's the number of free parameters in this hypothesis class. So this is sort of a parametric representation of your hypothesis class. It's helpful to keep in mind this particular parametric representation. So whenever I say feed forward neural network, I essentially mean that it is a function which is of the form say gk of wk of gk minus 1 wk minus 1 of some w1 x. Okay, let me, in general, you also have a bias, but one way of implicitly describing the bias is that your x is redefined to, let me call this x prime. So your x prime is x1. Okay, where each wj is a matrix of size dj cross dj minus 1. Right, and your non-linearities, which are also called the activation functions, so these are some non-linear functions. And these are specified as part of whatever the architecture of the neural network. So the only free parameters that you have, the only thing that you can freely choose to design your predictor are these WJs. Okay. Any questions?
So, TG plus one,
I'm sorry?
because times W is TG plus one.
So okay, yeah, you're right. So it should be dj cross dj plus dj minus 1 plus 1. So this should be r to the dj cross dj minus 1 plus 1. Any questions? Okay, if not, then we'll stop here and we'll continue the next class.